Hi, welcome to Lesson 3.4, Operations with Radicals. So we've seen radicals in the past, and it's basically the idea we need to work with exact values as opposed to using approximated values. So we're going to be, for the majority of this course, going to be just using the radical as it is as opposed to getting the decimal equivalent. So underneath the square root sign is the radicand, and any value outside here is the index. We're going to be just dealing with square roots, so generally the index would be a 2 there, but if it's a square root, the 2 isn't necessary, so we don't have to write that. So radical rules, we want to find out first of all if the square root of a sum is equal to the sum of the square roots. So we're going to use the left side and right side check. So we'll substitute 9 for A and 16 for B, and we'll see what happens here. So we put in the square root, so we'll put in 9 plus 16 here. 9 plus 16 would be approximately 25, and then the square root of 25 is 5. Then if we look at the right side, we're going to do the same sort of thing. Root of 9 plus the root of 16. Root of 9 is 3. Root of 16 is 4. 3 plus 4 is 7. Therefore, well, actually not therefore, since, I guess, would be the way to go about that. So since 5 does not equal 7, therefore the left side does not equal the right side, and therefore the square root of a sum does not equal the sum of square roots. Okay, so now let's move along, and I guess what can be concluded is that we're going to move along to multiplication now. So we'll do the same sort of thing. Left side is root of A times B. We'll substitute 4 for A and 25 for B. So we'll have 4 times 25. Take the square root of that. 4 times 25 is usually 100. And then we take the square root of that, and that gives us 10. Because 10 times 10 gives us 100. And then on the right side, we'll take the square root of 4, and we multiply by the square root of 25. The square root of 4 is 2. The square root of 25 is 5 on most days that end in y. And then when we multiply 2 times 5, we get 10. And lo and behold, we see that 10 does equal 10, since 10 equals 10. Therefore, left side equals right side. Therefore, the square root of a product is equal to the product of the square roots. Okay, so that's something that we're going to be needing to pay attention to in the next little while. Okay, so we can express radicals as mixed radicals, where the coefficient is just 1, so we can have, entire radicals, first of all, the square root of 12 with a coefficient of 1 out front, or mixed radicals where we have a coefficient that's other than 1, which would be 2 in front of the square root of 3 here, which is the same as 2 times root of 3. So if we look at this root 4 times root of 6, we want to express this as mixed radical and an entire radical. So mixed radical first, well, we take the square root of 4. We can see that 4 is a perfect square, so the square root of 4 is 2 times 6 just gives us 2 root 6. And then if we want to look at this as an entire radical, we just multiply 4 times 6 and we get the square root of 24. Actually, but this comes from the root of 4 times 6, because from the root of 4 times the root of 6 is the same as the root of 4 times 6, as we discovered up here, where the root of a product is equal to the product of the roots. The root of a product is equal to the product of the roots. and the root of 4 times 6 is the same as root of 24. So here is the mixed radical of this, and here is the entire radical of that. Okay, let's see a couple more examples here. So we want to change to mixed radicals in the simplest form, and a mixed radical is when we have the smallest number possible under the radical sign. So in order to do that, what we want to do is we want to identify what perfect square is in root 80 that we can pull out of root 80. So we want to see what product of two factors of 80 we can use where one of the factors is a perfect square. So what we could do is we could say, okay, well, obviously 4 times 20 gives you 80, and then that gives us the root of 4 times the root of 20, which the root of 4 is 2, and the root of 20, well, we got 20. However, if we look at that a little closer, we see that root of 20 isn't in simplest form either. We could actually, we know that 4 times 5 gives us 20, so what we could do is we could change 4 times 5, or 20 into 4 times 5, and so that would give us then, maybe, I don't know where I can write this, maybe up here, root of 20 is the root of 4 times 5, and that's the root of 4 times the root of 5, and the root of 4 is 2, and the root of 5 just stays as it is. So we've got 2 root 5 for the root 20, but we also have this 2 up front, and 2 times root 20 would be 2 times 2 root 5, and 2 times 2, so that, I'm making a mess here, we have the 2 root 20 from down here, and that gives us 2 times, 2 root 5, which gives us 4 root 5. Okay, so 4 root 5 is the simplest form of root 80. Now, if we were to square this 4, just to check, square this 4 and bring it back inside the square root, we would see that this is actually, if we square 4, we get 16 times 5, and 16 times 5, well, 5 times 10 is 50, 5 times 6 is 30, add them together, get 80. So, we have root of 80. So, had we recognized that in root 80, that was actually 16 times 5, then we could have done this in one step. We could have said, okay, well, root 80 is the root of 16 times 5. You break this apart into root of 16 times the root of 5, and the root of 16 is 4, and 4 times root 5, so that would be your final answer. So you can do it like that. Obviously you can do it like this too. You recognize 4 times 20 gives you 80, but because root 20 isn't the simplest form, we have to do that again. So we have to kind of do that process twice in order to find the simplified form of a root. So you really want to take a look at all the factors of the number that's underneath the square root sign, or the radicand, and see what the largest perfect square is that you can divide out of it. Okay, so we're going to do that for these next few. I was just showing you the long method, so just to show you that you can do it, but it's a lot more work. I mean, you kind of have to do it twice. So you want to look in 28, you want to see what two factors where one of them is the largest perfect square possible that you can divide out of 28. And so we get 4 times 7, which is square root of 4 times the square root of 7, and the square root of 4 is 2, so we get 2 root 7. And then you check and you look at root 7, and obviously there is no factors of 7 where 1 is a perfect square. Okay, so then you're done there. Okay, we'll move over here. we got 3 times root 12. We got the 3 outside, so let's just leave it. And then root 12, well, we want to see what the largest perfect square that can divide out of 12 would be. That would be 4 times 3. So we got 3 times root 4 times root 3. And 3 times, and the root of 4 is 2. And then so you end up getting 6 root 3. Then, of course, over here, we look at this, we got 6 times, well, 36 is a perfect square, so we just take the square root of that, and then you just multiply those together to get 36. Okay, moving right along. When we want to change to entire radicals, you're going to, because this value up front, this coefficient, has been pulled out of the radical in the first place, when you pull it out, it becomes a square root. You take the square root of it, which we did up here in these other examples. Whereas when we put it back in, we have to square it so it doesn't lose its value. So 6 is the same as the square root of 36, and that's multiplied by root 2. And then that's the same as the root of 36 times 2, which is the same as root of 72. Okay, over here, same sort of thing. We're going to bring this 4 into the radical, and the square root of, 4 squared is 16, and then this is the same as the root of 16 times 3, and 16 times 3 would give us 48. Same thing here for 3 and 7. Take the square 3, we get root 9 times root 7, which is root of 9 times 7, which is the root of 63. And then again here, square of 2 is 4, and then we've got the root of 4 times 11, which is the root of 44. Okay, so multiplying radicals, you group things together, you multiply the coefficients together, and you multiply the radicands together. Okay, and then try to simplify down the best you can. So here we're going to multiply the 3 times 2, and you're going to multiply the root 5 times the root 8. And so 3 times 2 usually is 6, and then we're going to multiply 5 times 8, which is 40. But now we see that 40 could be reduced down. So what we're going to do is we're going to leave the 6 out front, and then we're going to see what times, or what 2 factors would give us the largest perfect square. And largest perfect square there is 4. So root of 4 times root of 10 is the root of 40. And then 6 times 2 root 10 is going to give us 12 root 10. And if you look at 10, there's no perfect square factor of 10 to be able to pull out, so that's in the simplest form. Look over here for part B. Again, multiply negative 3 times 3 and 18 times 3. So we get negative 9 times the root of, what would that be, 54. And so now what we're going to do is we'll look at 54 and see what perfect square can be pulled out of that. And so that's negative 9 times 9 times 6, which is negative 9 times the root of 9 times the root of 6. Root of 9 is 3, so negative 9 times 3 root 6. 6. And that gives us negative 27 root 6. And you look at 6 inside the radical, and we can't simplify that anymore because there are no factors that are perfect squares that could be divided out of that value there. And adding and subtracting, we have to reduce the radical into simplest form, and we add and subtract only like radicals. So pretend as though they are x's and y's, or x squareds and y squareds, or whatever that may be. Whatever the radical is, if it's a like radical, then you can add them together or subtract them. Otherwise, you cannot. Okay. Same number under the radical, so root 6 and root 6, etc. And we just subtract the integers out front. So 3 root 6 and minus 2 root 6, you just take the 3 and the minus 2, you subtract those, and then leave the root 6. Okay, so let's take a look at a couple examples here. So we got 3 root 2 plus 4 root 2, negative 5 root 3 minus 6 root 3. Well, conveniently, they're already grouped into like terms. So 3 plus 4 would be 7 root 2, and then negative 5 minus 6 is negative 11 root 3. And here we can't do anything more because root 2 is not the same as root 3, so we can't combine those any further, so that's where that ends. And for part B, we've got 2 root 27. Well, 27 we see is a fairly large number. Let's see if there's any perfect squares that can be divided out of that. And I would have to say that 27 is made up of 9 times 3. We'll leave 2 root 3 there. And that's another clue also. Here's a root 3. Oh, there's a root 3 right there. So it looks like we're on the right path here. And then here's a root 5, so chances are that root 20 can be broken up into 4 times 5. And then we'll just pull this root 9 out, which is 3. And then that 4 gets pulled out as 2 root 5 minus 2 root 5. And then this gives us 6 root 3 minus 2 root 3 plus 2 root 5 minus 2 root 5. There's a bit of a zero pair, that's gone, and then 6 minus 2 is 4 root 3. And like they say, Bob's your uncle. Alright, so you have the rest of the class to please finish off all these questions, and we will take them up next day in class. Thanks for watching, and have a great day.